Hi, my name is Per Avset. I'm a geophysical advisor with Televoil Norway. I'm also a adjunct professor at Norwegian University of Technology and Science in Trondheim. Today I will give a talk with the following title: Seismic Screening for Hydrocarbon Prospects Using Rock Physics Attributes. I'll start with an outline of my talk. First, I will give a short intro, just an overview of the techniques of using AVO inversion in combination with rock physics template analysis during a quantitative interpretation. I will show you some of these rock physics attributes that I'm presenting here, the methodology behind and how these can be used for seismic screening. Then I will go on and show some examples, and I will demonstrate the use of these on well log and seismic inversion data from a Norwegian Sea gas discovery field. Briefly at the end I will go through some of the pitfalls and finally also conclude my talk. AVO inversion is of course a big topic, and I will not go into the details, just show a brief introduction to this technology. So this is a slide I call AVO inversion in a nutshell. So when we have gathers, pre-stack gathers, there's a lot of information that can be very valuable to extract from these gathers, and seismic AVO inversion is a way to estimate elastic properties from these gathers. And using approximative AVO equations, for example, Fermat-Hiltermann's that I'm showing here, we can actually estimate acoustic impedance and VPVS from these gathers. And we usually use the angles up to about 30-40 degrees, sometimes higher if you will also want to term a third AVO term, which also can give you information about the density. In this talk I will focus on the use of impedance and VPVS. To the right in this slide is some examples of acoustic impedance and VPVS estimated from the gathers that we see to the left. When we invert for layer properties from pre-stack gathers, we are actually going from contrast to layer properties. And this slide is also just a very brief explanation, very conceptually, showing how we do that. When we have a seismic trace, we see wiggles, and these wiggles representing reflectivities or contrast in the underburden. And in order to get the layer properties out, we need to do a deconvolution. We need to have an estimate of the wavelet, and take away the wavelet effect, estimate reflectivity series, and then we invert during some kind of integration algorithm to get the relative impedances. And then if you add a low frequency trend to that, we can actually get the absolute values. Of course, in a real AVO inversion, it's done in a more sophisticated way, where the low frequency model is the starting model, and it's iteratively updated to fit our seismic data, and finally we end up with our best estimate of the impedance values. And this can be done both for the acoustic impedance and the VPVS ratios. Then, having estimated the impedance and VPVS ratios, we can start to look at these two in a crossplot domain, and that allows us to use rock physics models to interpret these data. We have established what we call rock physics templates, and these are handy and useful to do this interpretation. So we make template or rock physics models for different lithologies and fluid scenarios. And here is a schematic illustration showing that different lithologies and different fluid scenarios will plot in different areas of a rock physics template. The goal of this presentation is to create some attributes that manage to extract the fluid information and the rock information or lithology information and separate those into different attributes. And I will show you now how we can do that. So here is a slide. In the upper left, you see a sandstone model for different porosities, but also for different fluid saturations. We have a water saturated trend, and for different porosities, we have used Gassman to estimate the effect of adding hydrocarbons, let's say gas, into the pore space for any given porosities. And you see this is a very nonlinear curve. It's not a straight line. So for low impedances, we can have a water-saturated sand with very high VPVS, and this is related to the fact that when you have a loose sand, not very well compacted, water sands tend to have high VPVS ratios relatively to more consolidated rocks. If you add hydrocarbons, we see that the hydrocarbon effect is a decreasing VPVS and a decreasing impedance. The attribute that I make is shown in colors. So what I call the fluid impedance shows that when we have data falling below in the direction of the hydrocarbons in that crossplot, which will be the warm colors, yellow and red, that becomes an attribute that can highlight the effect of hydrocarbons. To the right, upper right, we see a different attribute where the colors are rotated almost orthogonally to the fluid trends and the fluid impedance crossplot. We call this the rock impedance. And now you see that the colors are showing a completely different trend. And it turns out that these are following more the constant shear impedance trends. And they should not correlate much with the hydrocarbon saturation changes. However, they will correlate very much with rock stiffness or porosity changes. So here we have separated the information in these crossplots into a fluid attribute and into a rock stiffness attribute. And we can call these fluid impedance and rock impedances. So we can even make a crossplot of these two different attributes in the new domain. And I'm not going into the mathematical details, but just saying that we can quantify these as a distance away from a defined background trend, which is given by this equation. And instead of plotting an attribute, a crossplot of impedance and VPVS, as we show in the lower left, we can transform it into this new domain where you have the crossplot of the fluid and rock impedances. Sometimes I also refer to the fluid impedance as CPEI, which is formerly been named as the curved pseudo-elastic impedance, whereas the rock impedance I often also refer to as the PEIL, the pseudo-elastic impedance for lithology. And you see in the latter one, it's a vertical change when you have a rock stiffness and a horizontal change when you have a fluid change, pretty much. So it became a very nice orthogonal separation of fluids and rocks. So let's test this now and look at some well log data. So this is an example from a well in this gas field in Norwegian Sea. To the left, we see some well log data. The leftmost log is the gamma ray in green and saturation in red. The second one is the acoustic impedance log, derived from PV velocity and density. And the third one is the VPVS ratio, derived from sonic measurements of PV velocity and shear wave velocity. So now, since we have the acoustic impedance and the VPVS ratio, we can crossplot all these data into a rock physics template. And that's done to the right. And then I've defined these attributes, which are fitting functions to these rock physics models. And as I showed in the previous one, they will measure the rock information in the upper one in colors, and in the lower right, you see this fluid impedance. And the hydrocarbons are shown nicely in the hot colors, plotting in a template where we see the data are plotting off this water-saturated sandstone trend, as we expect. We can plot these attributes back into the log domain, and that's shown in this slide. So now I juxtapose these to the original well log data that I had in the previous slide. And I see this rock impedance, or the rock stiffness, in the first color panel. And you can see that there is a very soft event in the beginning, but then it's gradually stiffening. And you see no effect of this hydrocarbon zone indicated by the dashed lines, where you also have high gas saturation in between. However, the fluid attribute is detecting the hydrocarbon zone very nicely. And you see the warm colors between these dashed lines corresponding very nicely with the resistivity or the saturation information on the logs to the left in the red curve. This slide just shows some crossplot where I validate these attributes that I just estimated against some other well log attributes that I've estimated that are more physical. And to the left is the crossplot of this fluid impedance, or the CPEI, versus the deep resistivity, or the logarithm of the deep resistivity. And you see that there's kind of a cutoff around 6.5 or 7, where the resistivity increases dramatically. So you see it's cutoff where all the values below that correspond with warm colors of and the colors in that display represent the fluid impedance attribute. To the right is a crossplot of the shear impedance versus this lithology or rock impedance attribute. Here I only included the sandstone data in that reservoir zone. The colors in that crossplot is actually the fluid impedance. And you see that the warm colors are plotting on top of the cold colors. And that's exactly what we are expecting, because the shear modulus should be insensitive to the fluid information. So this shows a very linear and nice match between the rock impedance and the shear modulus estimated from these well-log data. So it just confirms that this attribute is very nicely correlated with the rock stiffness information and has no fluid information. So now we can conclude we have separated the fluid information and the rock information, and we demonstrated that on these well-log data. So let's have a look at the seismic inversion data. So here is an example from the same field. It's a different well, but it's the same area. And the seismic inversion data are shown. To the left is acoustic impedance, estimated through a seismic AVO inversion. And also we have the VPVS ratio to the right. And there is a well going through a fault block, and there is a hydrocarbon accumulation that we might see on the VPVS especially. You can see there is a flat spot indicated with very low VPVS ratios right above, but we also see some low VPVS ratios below the flat spot. So there's not a unique information in terms of the fluid. Let's try to convert these impedance and VPVS into these new attributes, because we know that both acoustic impedance and VPVS ratio are both affected by rock effects and fluid effects. So they don't really separate out those two. Now I show you the new attributes that I estimated. To the left is the rock impedance, and to the right is the fluid impedance. And now you see very nicely on the fluid impedance these warm colors in the reservoir zone and the flat spot, and there is no indication of hydrocarbons below the flat spot. To the left, we only see the rock information. There is no information about the fluids, and you see there's in general a compaction trend with depth, which we expect, but there are also changes related to the positional cycles of stratigraphy at a higher resolution. We can go more into the detail and have a look at this well and compare these attributes at the well location. Now I will focus on the fluid impedance only. So you see here this nice accumulation above, and there's a flat spot, corresponds very nicely with what we see in the well-log data. So, and the rightmost plot actually superimpose the fluid impedance estimated from the seismic inversion data at that well location on top of the same fluid impedance attribute estimated from the well-log data in white curve, dashed line. And you see they are fitting quite nicely. Unfortunately, we only have well-log data starting exactly from the reservoir top and down. But you see it's a nice match. Of course, the well-log data has much higher resolution. If you go down flank from that flat spot and just pick a trace, and let's call that the Saudo well location, we would expect that to be a water response through the same stratigraphic level, assuming that it's still a sandy layer. And we see here that the water response is picked up, and it doesn't show the same warm colors as we saw above the flat spot contact. Let's cross-plot these data back into the rock physics template and have a look more detail. This is the well-log data from this well too, and we see that the gas zone is plotting nicely with warm colors of fluid impedance in the rock physics template area where we expect the hydrocarbons to plot, just below the brine sandstone model trend. Rest of the data in the well log is plotting on the other side, which will be mostly water sand, shales, and maybe some carbonates. The inversion data at that same location show very nicely the same pattern. Of course, the resolution is lower, so you see less data points, but the location, again, the reservoir zone is plotting very nicely in the hydrocarbon area of the template. Let's have a look at this down flank water zone, or where we expect the water zone to be. And lo and behold, you see that zone of the same stratigraphic level is plotting just above the water saturate trend of the rock physics template model, as expected. And there are no warm colors in the data at this location. And this slide shows an example along a random line where I also estimated this fluid impedance and rock impedance. And this random line is going from well 1, it's almost projecting through well 2, and then to well 3 at the other end. And the upper one shows a fluid impedance attribute. And we see there is a nice anomaly at well 1, which is actually a gas discovery. There is also a gas accumulation at well 2, which was the one we just looked at. And there's also an interesting anomaly between those in the syncline. And there are also fluid impedance anomalies deeper down between well 2 and well 3. However, at well 3, there was a thick hot shale located. And that one does not show a fluid impedance anomaly. If we look at the rock impedance attribute below, you see that the well 3 location where we have a hot shale, it's actually a much softer response compared to what we see at well 1 and also the fault block where well 2 is penetrating. If we look at these data in a crossplot, and here in this crossplot we show big squares are inversion data at well locations and also from an anomaly between well 1 and well 3, whereas the small circles are well log data. And here we see that well 1 is plotting nicely both well log data and inversion data into the area of the template where we expect hydrocarbons to plot in the lower left. We also see that some of these interval anomalies are plotting in the area of the template where we expect hydrocarbons, but at higher impedances. This is expected because they are more deeply buried, so we expect that there is some compaction trend. So they will shift it towards higher impedances. If you look at the data from well 3, both the inversion data and the well log data, you see they are plotting at relatively low impedances, but they also have higher VPVS ratios, and the data are plotting consistently above the water saturated brine sandstone trend. And we know that the hot shales in this area are immature in this well, so we don't see any overlap between the hot shales and the hard carbon filled sandstone, which is, of course, in terms of prospectivity hunting in this area, is valuable information. This procedure, both the use of seismic AVO inversion data and the use of rock physics templates, of course there are many pitfalls and uncertainties. I will not go through these in details, but I've listed some here and I also highlighted some of those that I think are the most important ones, especially for the case that I've showed. And one that I want to highlight is, of course, poor well ties and wavelet estimation uncertainties. In these areas, we had quite a good well ties. Anisotropy is, of course, an effect that can affect your AVO, and also in the rock physics templates, we have assumed isotropic rocks. We know that hot shales can be highly anisotropic, also shales, and that's something that can also affect your AVO data and the interpretation of these. The low frequency model used for the inversion is also something that can pose some uncertainties. Of course, if you have wrong rock physics models and input parameters used for the rock physics models, so it's very important to have a good, well-calibrated rock physics model. And we have done that. We have validated the rock physics model to well logs in the area that I showed on this North Norwegian Sea case. One of the biggest pitfalls, of course, in any of these seismic AVO applications is the fact that low gas saturation can give almost exactly the same impedance and VPVS values as commercial gas, so that's always a pitfall in these type of studies. Geological variabilities and rock physics uncertainties. We know that when we have two observables, there will always be non-uniqueness by the fact that there are many, many more geological factors that can move in different directions in this crossplot. And I mentioned the low frequency model and the wavelet effects, which are maybe the two key uncertainties in AVO inversion. Of course, if we have a good low frequency model and an optimal wavelet, our data points should be interpreted according to the template, and we would be able to detect these hydrocarbons nicely if they're well resolved. But if you have a poor wavelet, even though your low frequency model is wrong, these data points can easily fall in the wrong areas of this template, and they will be interpreted erroneously. You could have the right wavelet, but if you have the wrong low frequency model, you can also miss a good opportunity to find hydrocarbon reservoirs. So finally, I want to conclude. Based on rock physics models, we have defined some useful attributes for screening and fluid softening and rock stiffness from seismic AVO inversion data. The attributes have been validated on well log data and applied to seismic inversion data from a Norwegian Sea gas field, and we have proven discoveries have been nicely identified. The rock physics-based attributes presented here will be easy to implement in seismic interpretation or petrophysical softwares when both acoustic impedance and VPVS are available. Finally, I want to end this talk with a quote. 30 years ago, John Claerbout wrote in his famous book, "Seismic inversion should be used like a lamppost, to light the way, not to lean upon." I think that we 30 years later should say, seismic inversion integrated with rock physics and geology can be used like a lamppost to light the way and to lean upon. Finally, I want to thank some of my colleagues at Tullow Oil, especially Tor Vegland. I also want to thank QL Labs for the AVO inversion data used in this study. And I also want to thank Ivan Lehosky at Geospace for valuable input. Thank you very much.